we can compute this maximum likelihood estimate by using the EM algorithm. So in the E step, we now have to introduce more hidden variables because we have more topics. So our hidden variable Z now, which is a topic indicator, can take more than 2 values. Specifically, we'll take k+1 values with B denoting the background and 1 through k to denote all the k topics. Right? So now the E step, as you can recall, is to augment the data and by predicting the values of this hidden variable. So we're going to predict for a word whether the word has come from one of these k+1 distributions. This equation allows us to predict the probability that the word W in document D is generated from topic theta sub j. And the bottom one is to predict the probability that this word has been generated from the background. Note that we use document D here to index the word. Why? Because whether a word is from a particular topic actually depends on the document. Can you see why? Well, it's through the pies. The pies are tied to each document. Each document can have a potentially different pies. Right? The pies will then affect our prediction. So the pies are here. And this depends on the document. And that might give a different guess of a word for a word in different documents. And that's desirable. In both cases, we are using the Bayes rule, as I explained, basically assessing the likelihood of generating word from each distribution and then just normalize. What about the M step? Well, we may recall the M step is to take advantage of the inferred Z values to split the counts and then collect the right counts to re-estimate parameters. So in this case, we can re-estimate our coverage probability. And this is re-estimated based on collecting all the words in the document, and that's why we have the count of the word in the document and sum over all the words. And then we're going to look at to what extent this word belongs to the topic theta sub j, and this part is our guess from E step. And this tells us how likely this word is actually from theta sub j. And when we multiply them together, we get the discounted count that's allocated for topic theta sub j. And when we normalize this over all the topics, we get the distribution over all the topics to indicate the coverage. And similarly, the bottom one is to re-estimate the probability of a word for a topic. Now in this case, we're using exactly the same count. You can see this is the same discounted count. And it tells us to what extent we should allocate this word to topic theta sub j. But the normalization is different. Because in this case, we are interested in the word distribution, so we simply normalize this over all the words. Right? This is different. In contrast, here we normalize among all the topics. It will be useful to take a comparison between the two. Right? This gives us different distributions, and these tells us how to improve the parameters. And as I just explained, in both E-step formulas, we have a maximum likelihood estimate based on the allocated word counts to topic theta sub j. Now this phenomenon is actually a general phenomenon in all the EM algorithms. In the M step, you generally would compute the expected count of event based on the E-step result, and then you just collect the relevant counts for a particular parameter and re-estimate it, normalize it typically. So in terms of computation of this EM algorithm, we can actually just keep counting various events and then normalize them. And when we think in this way, we also have a more concise way of presenting the EM algorithm. It actually helps us better understand the formulas. So I'm going to go over this in some detail. So as an algorithm, we first initialize all the unknown parameters randomly. Right? So in our case, we are interested in all those coverage parameters, pies, and word distributions, thetas. And we just randomly normalize them. This is the initialization step. And then we will repeat until likelihood converges. Now, how do we know whether likelihood converges? we're going to compute the likelihood at each step and compare the current likelihood with the previous likelihood. If it doesn't change much, and we're going to say stop, right? So in each step, we're going to do E step and M step. In the E step, we're going to augment the data by predicting the hidden variable values. In this case, the hidden variable Z sub dw indicates whether the word in W in D is from a topic or background, and if it's from a topic, which topic. So if you look at the E step formulas, essentially we're actually normalizing these counts, these probabilities of observing the word from each distribution. So you can see basically the prediction of a word from topic theta sub j is based on the probability of selecting that theta sub j as a word distribution to generate the word, multiplied by the probability of observing the word from that distribution. And I said it's proportional to this because in the implementation of EM algorithm, you can just keep a counter for this quantity, and then in the end you just normalize it. So the normalization here is over all the topics, and then you will get a probability. Now in the M step, we do the same, and we are going to collect these allocated counts for each topic, and we split words among the topics, and then we're going to normalize them in different ways to obtain the re-estimate. So for example, we can normalize among all the topics to get the re-estimate of pi, the coverage, or we can renormalize based on for all the words, and that would give us a word distribution. So it's useful to think of the algorithm in this way, because when you implement it, you can just use variables to keep track of these quantities in each case, and then you just normalize these variables to make them a distribution. Now I did not put the constraint for this one, and I intentionally leave this as an exercise for you, and you can see what's the normalizer for this one. It's of a slightly different form, but it's essentially the same as the one that you have seen here, namely this one. So in general, in the implementation of EM algorithm, you will see you accumulate the counts, various counts, and then you normalize them. So to summarize, we introduced the PLSA model, which is a mixture model with K unigram language models representing K topics. And we also added a predetermined background language model to help discover discriminative topics, because this background language model can help attract the common terms. And we show that with maximum likelihood estimate that we can discover topical knowledge from text data. In this case, PLSA allows us to discover two things. One is K-word distributions, each representing a topic, and the other is the proportion of each topic in each document. And such detailed characterization of coverage of topics in documents can enable a lot of further analysis. For example, we can aggregate the documents in the particular time period to assess the coverage of a particular topic in a time period. That would allow us to generate the temporal chains of topics. We can also aggregate topics covered in documents associated with a particular author, and then we can characterize the topics written by this author, etc. And in addition to this, we can also cluster terms and cluster documents. In fact, each topic can be regarded as a cluster. So we already have term clusters, and the higher probability words can be regarded as belonging to one cluster, represented by the topic. Similarly, the documents can be clustered in the same way. We can assign a document to the topic cluster that's covered most in the document. So remember, pies indicate to what extent each topic is covered in the document. We can assign the document to the topic cluster that has the highest pi. Okay? And in general, there are many useful applications of this technique.